Hello, honey bun. Did you get that stuff done?
Hey, Dr. Riley.
College apps
So, huh?
College apps done?
Yes, they're done. I finished on Monday,
Good.
which is a relief. But I just wanted to let you know that my period came today and my cramps are debilitating right now, so
Oh,
I don't think I can do class.
okay. You want to
I'll have
link and listen?
Hmm?
Well, how do you want to handle this? Because I want to make sure you get the material. Want me just to send you the link?
Yeah, I think if I have to contact the office, I'll have my mom do that, but I just got really sick and I physically can't do anything right now, but I'll contact like Jonathan or something and have him.
Well, I will send you the link to the video for the class. How's that sound?
Oh, yeah, that would be great.
Okay. So
yeah, that would be very helpful. Thank you.
So let me mark you absent, all right? But I'll send you the link and then just go and do the things that make you successful. Did you take Tylenol or something right
away? Yeah, but they just exited my system, so I'll take more.
Oh gosh, yeah. You just can't.
Yeah.
Yep. Remember those days. Well, go ahead, lie down, do your thing. Tomorrow will be a better day.
Thank you.
The day after that'll be better.
I guess. Thank you. I guess my mom will just contact the office and let them know so I'm not marked absent.
You can't listen to the lesson, just listening.
Mom, she said she's gonna send me the video.
Okay.
Yeah.
Okay.
Okay. Thank you so much, Dr. Riley.
You're welcome. Bye, Heather. Feel better.
Bye. Thank you.
Bye. You're welcome. Everybody in. Okay, I think we have just about everybody here.
Hi, Dr. Riley.
Hello. How's it going, David?
I'm good.
Very good. Okay, so let me just start putting attendance in. I have David, do you have two devices, honey?
Sorry?
Do you have two devices? Because it's saying that you're still trying to join.
That's weird. I was on my phone. No, I tried joining on my phone and then I updated the app and then I joined again and now there's two of me in here.
Yes. Well, one of you is struggling to get in.
There's 3 of me?
Let's see how many do I
Wait.
have. I have 1 in, and then I have 1 trying to join. So stop bilocating, David.
You can just remove the one that's not talking in here.
But I can't because you're not really in. So you're kind of in that limbo world.
That's weird.
Because you're in the waiting room. So
I'm gonna leave and come back and let's see what happens.
Okay. In the meantime, I'll start putting attendance in. Okay,
What
I think you've connected your body and soul again.
All right, that's good.
Okay, so let me just get attendance up and in. Okay, so do I have Trace? I do. Present. And do I have Miles? I do. Present. And Ben. I don't see Ben, so I don't have Ben yet. Okay, I have Sheldon. I have. Okay, so I don't have Victor yet.
I'm in here.
Oh, you are there. There you go. Thank you. Okay, I have Katie. I have Sophia. I have Gavin. I have Jonathan. I have Olivia. I have Wyatt, who's first on stage here. I have David. Do I have Jordan? Yes, I do. Okay, Heather I know is out. Mason I have. And Maisie I have. Okay, so I'm still missing a couple of people. So I'm missing Ben. Ben's the only one I'm missing that I want to have. Okay, so let me just put attendance in and I'll update that if Ben comes in. Okay, so this is our plan. Today we're gonna look back at the 1.8 and just kind of go over that a little bit, the ones that we hadn't gotten a chance to finish yet. So let me get that up and going. So let me just get my thing. Okay. So tell me what we didn't do on this exploration activity. What do we need to go over as a class? So was it?
We only did the first stage.
Okay, so we're going to do 3 and 5 right now. Okay, so let's do that together. So this is what I'm seeing. When I look at 3, oh, let me show you what I have. So let me just share my screen. And there is Ben. Okay, so let me admit Ben, and let me quickly update the attendance. Okay. All right, so that's good. Okay, so now let me go back into. Okay, so we started out with velocity and acceleration. So for the quiz, you need to know that if I give you a position function, the first derivative is velocity and the second derivative is acceleration. So what is the object's initial position? So the initial position happens where time is 0. So if I put 0 in, what I'm really trying to figure out is d of 0. So if I do that, I'm going to get 10 times 0. So 10 times 0 plus 5 over 0 plus 1 minus 5. I end up getting 0 as my position. So 0 meters, because I gave you units. So 0 meters are where I initially start out. So then the next thing it says, at what velocity is the object moving at the end of 4 minutes? So what I really want to figure out is d prime of 4. That's my goal. Okay, and in order to do that, I'm going to take the first derivative. So let me just stop sharing and reshare because I'm getting very glitchy over here. I think it was from flipping into the attendance. So let me try this again.
Dr. Riley, I have a question.
Yep.
For that one you just did, wouldn't the starting position be -5? I don't know if that makes sense, but if you plug it in, doesn't that -5 at the end affect it?
It does, but doesn't it balance out the +5? So isn't this 0 plus 5 minus 5?
Oh, yeah. Okay.
Okay. All right. So then to do the first thing, what I would do is I would not do the quotient rule for that second term. So I'm going to first write it so that I can see what I'm doing. So this is 10t plus, I'm going to bring this up to the -1 power. Just because you know a rule doesn't mean it's always a good idea to use it. Okay, in this situation, because you have a constant in the numerator, it is infinitely easier just to go ahead and bring that little denominator down up as a -1 and then start taking the derivative from there. Okay, so here's my derivative. Now remember, use good notation so you keep track of what you're doing, because you're going to be in the world of doing multiple derivatives. So you don't want to mess up on the notation because that will really make things confusing. So this is 10, and now this is going to be -5 times t plus 1 to the -2 times the derivative of the inside, which is times 1. I'm going to still put times 1 down initially so that I know that I'm practicing doing the chain rule. Okay, now I am going to evaluate this at 4, and in order to do that, I first want to get this in a situation where it makes sense. Having it raised to the -2 power makes no sense in terms of evaluation. Okay, so that's a better form. Here's your 4. 10 minus 5 over 4 plus 1 is 5 squared, right? So 4 over 5 over 25. So 10 minus 1/5 is 9 4/5 meters per minute. Okay, so that's my first derivative evaluated at 4. Anybody have any questions or concerns about that? This should seem pretty straightforward, pretty easy. The problem 5 is a little bit more challenging, especially when we get down to C and D. Okay, acceleration. Again, you have to know that acceleration is the second derivative. I'm going to take my first derivative and rewrite it here in the form that is good for me to work with. Okay, that would be that form. Okay, I don't need the times 1. Now take that second derivative. This is hashtag. So that's going to be +10, and then this is going to be t plus 1 to the -3 times 1. And again, I'm going to rewrite that without having the negative exponent because I know I have to evaluate it. So then I have t plus 1 cubed. And if I have t plus 1 cubed, then that's going to give me the d prime of 4 equals 10 over 5 cubed, or 10 over 125 minutes per meter. And you can, reduce that if you want, 2 over 25 minutes per meter. I would not make it a decimal. It's fine the way it is. And that would be your acceleration. Okay, so those are the kind of things you need to be able to do Plus, you need to answer such things as at what time is the velocity something? So you would first get your derivative, set it equal to the velocity, and then solve for time. So just understand the wording. RB said at what velocity is the object moving at the end of 4 minutes? They're looking for a velocity, not a time. They gave you the time. So read these types of questions carefully so that you know that you're answering the correct thing. Know whether you need to have a time or need to have a velocity. Your units should be, oh, and this, I'm sorry, this should be meters per minute squared. Sorry, so that should be squared in the bottom. So I'm just gonna say that. Make sure your units are correct. Okay, acceleration is squared units, meters per minute squared. Velocity is straight up minutes per meter. Okay, initial position is just meters. So make sure if I give you units that you're giving me back units. Okay, so I thought this last problem was good. It kind of bridges what we're doing now with what we're going to be doing in chapter 2. So that's why it's worth going through. So in terms of C and D, so C and D, those kind of problems will be on your plate in the future, not on this current quiz. Okay, this current quiz is only gonna handle like up to A and B. Okay, so let's get through this. Okay, so find the expression for how the velocity of the car changes over time. Okay, so we're just gonna take your first derivative. Okay, I'm just gonna do this myself in the interest of time because we have other things we're gonna do. And that's done. That's my first derivative. That's velocity. Find an expression. All they're asking you to do is find the second derivative now, 6t minus 4. Okay, so I have both of my expressions. When I do a C and D, I'm going to use these derivatives. So it says find the time interval for time is greater than or equal to 0 when the car is going forward and when it's backing up. So when the car is going forward, velocity is going to be greater than 0. When it's backing up, velocity is going to be less than 0. When it's not moving, velocity will be 0. Okay, so those are the things you want to understand. So what I'm going to do is I'm going to take that first derivative and I'm going to factor it because really the 0 is kind of the jumping off point. I need to know when it's 0. So let's set that up. Okay, so if I'm going to factor that, I'm going to do hard factoring. So that means I'm going to say to myself what multiplies to 21, to negative 21, and adds to a negative 4. And my answer to myself is going to be a negative 7 and a positive 3. So I'm doing decomposition. You can do factoring any way you want to do it as long as you can do factoring. So this is 3t minus 7 plus another 3t minus 7. I need a 1 here. So my factors end up being t plus 1 and 3t minus 7. So what's going to happen now is I'm going to figure out, I'm going to kind of do a sign chart of sorts. I'm going to figure out what's happening with this function. So if t is negative 1 or if t is 7/3, that's where my velocity is going to be 0. What happens when t is 0? If I plug in 0, I get a negative. So therefore, my first derivative looks like this. Okay, so now I can answer the question. So the velocity will be less than 0. Where? What should I say? Let me think about this. So where will velocity be negative?
Wait, can you explain quickly how you drew that parabola?
Oh yeah. So I plotted the roots. See, these are the roots. And I got them by setting my factors equal to 0. So t plus 1 equals 0 at 0. Or at negative 1, excuse me. And 3t minus 7 equals 0 at 7/3. So this is my line for velocity.
Okay.
Okay, so velocity is the vertical axis. And the horizontal axis is time. So this is time. So when I should do one more thing, since they want to know, find the interval where t is greater than or equal to 0, I need to figure out what it is at 0. So 0 is going to be, what did I say? At time is 0. It's going to be -7, right? So if time is 0, so plug in 0, you get a -7. So what's really happening here is where time is 0, so this is 0, this is -7, is going to be my y value. So I'm probably confusing things here. So let me just get rid of that and clean this up. So this is t plus 1. So what I did was I factored this. Second equals to 0, where does that happen? It happens at -1 and 7/3. I'm talking about the interval where time is greater than or equal to 0. So 0 is right here. This is where time is greater than 0. So I need to figure out what's going on to the right of that. Okay, all of this area to the right is in play. So what I'm seeing right away is that the velocity is negative when time is between 0 and 7/3. I can include 0. I can't include 7/3 because 7/3, my velocity is actually 0, not less than 0. The velocity is then greater than 0 the second I get beyond 7/3, all the way to the end of my function or the end of time. So what they're doing, this is your introduction to how you think about sign charts. And I'm looking at my first derivative and I'm seeing where it's negative and where it's positive. So where it's negative, so let's just do this. This is where velocity is negative. Where it's yellow, it's positive. Where it's above yellow, the purple is positive. So here's my purple. Here's my orange. And that's my interval notation. So by analyzing the roots or the factors of my first derivative, I can make determinations about when my velocity is greater than 0 or less than 0, and therefore I know when the car is going forward and when it's going backwards. It's going backwards every single time that the velocity is 0. Now they wanted us to talk about time being greater than or equal to 0 because you really can't have negative time. So that's why I'm not using the values that are to the left of time is 0. Even though velocity is negative there, it's not really germane to our discussion because we can't deal with negative time. Does that kind of make sense? Silence.
I have a question.
Uh-huh.
Couldn't you include 7/3 because it says equal to or greater than 0?
So you're confusing two things. It says time has to be greater than or equal to 0. For the car going forward, velocity has to be greater than 0.
Oh,
okay. Time going backwards, the velocity has to be less than 0. So that's why I don't include it. So at 7/3, the car is actually stopped.
okay.
Okay, but that was a very, very good point. So at 7/3, velocity is 0, which means it is stopped. That's different than the time factor.
Also, the orange is when it's backing up and the purple is when it's moving forward, right?
Yes, exactly. Because velocity is negative in the orange and is positive in the purple. Okay, so now question D, I thought that was interesting and that's why I put this on. This is kind of a reach for what we're doing right now. But the second video addressed this and it talked about the fact that a car is speeding up when velocity times acceleration is positive. When velocity times acceleration is negative, it's slowing down. So what I did was the following. I set up a little chart. And first off, I used my second derivative. So I'm going to use both derivatives. So let me write them both here. Oops, not like that. Okay, my first derivative is going to be this, and that in factored form was this, and that was the helpful form for me. My second derivative is going to be 6t minus 4. Okay, so it says find the intervals where time is greater than 0 when the car is speeding up or slowing down. Okay, so how do I want to explain this? So there's a couple of things going on here. When I set my acceleration equal to 0, that happens at time is 2/3. Okay, so I'm going to deal with time between 0 and 7/3, but I'm going to also consider what's happening at 2/3 because that's where the acceleration is 0. Okay, so I'm going to use those marks as my limits, if you will. So what I want to know is what's my velocity between 0 and 2/3. So 0 and 2/3 is the orange. It is negative. What's my velocity between 2/3 and 7/3? I'm still in the negative. And then beyond 7/3, my velocity is positive. Okay, so I've gotten those 3 values. This is like a sign chart. So now what's the signs associated with acceleration over the same time period? So between 0 and 2/3, so let's plug in 1/3. At 1/3, 6 times 1/3 is 2. Acceleration is going to be negative. On the other side of 2/3, it's going to be positive, and it's going to always stay positive. Okay, so now I want to know the product. So this is going to be the net result. So if I multiply negative velocity times negative acceleration, I get a positive net result. Negative velocity times positive acceleration, I get a negative net result. And positive times positive, I get a positive. Wherever I have a positive net result, my car is speeding up. And wherever I have a negative net result, my car is slowing down.
Where did you get the positive and negative values for the acceleration part?
So I took this function right here and pick a number between 0 and 2/3 to evaluate it. I picked 1/3. So 6 times 1/3 minus 4 is 2 minus 4, which is -2, right? So that's a negative. That's where this negative came from. Then pick a number greater than 2/3, but less than 7/3. So pick 1. 6 times 1 is 6, minus 4 is a +2. So that's where this positive came from. And then whenever I use anything beyond that point, it was still positive.
That makes sense. Thank you.
Okay, so that's the second video. The guy does exactly this. So I thought it was neat to apply it to this situation. So this is kind of, you're thinking about what's going to happen in the future. So don't worry about this for the quiz, but I wanted you to at least see this once before we actually get into it. And I wanted to give you a good reference. And I thought those 2 videos were pretty good. So this first one really is more what we're going to be doing. This second one takes in what's going to go on in chapter 2 and beyond. Okay, so that's all I want to do with this little thing. So what I want you to talk about now with me and think about is how are you situated for this quiz coming up? So what will be on it? So I'm going to definitely have you evaluate a function, a derivative of a function for a trig angle. So you're going to have to need to know how to use your unit circle. Okay, I'm going to assume that you're going to be using a unit circle or creating your own, which is actually preferable. You have to give me an exact answer and you have to show your work. So you can't just use a calculator. So if your MO is to go to a calculator to get these trig values, that would probably not work for you. Okay.
Wait, could you repeat that first part really fast? I missed it. I'm writing it down.
Yeah, so in terms of what's on the quiz. So what I said was, I'm going to have you evaluate derivatives of functions, Okay, you're going to have to evaluate them for numbers and also for angles on the unit circle. So that means that you have to know how to take your derivatives in trig, and you have to know how to use your unit circle to evaluate them. Okay, so the best examples we had from that in recent history is the problems that we did in 1 and 2. Okay, so those had good examples for us, and we worked them through the other day. So that's what I want you to go back over and look at that. Things that you want to keep in mind is, for example, if I say, let's just say our function equaled sine 3x, okay, and I want to find f prime of x and then evaluate it where x equals pi over 2. Okay, so what you would do is you would find your first derivative, which is going to be 3, would be a negative 3 cosine 3x. Okay, now this is where people run into problems. I'm telling you that x is pi over 2. I'm not telling you your angle is pi over 2. You've got to figure this out by plugging in pi over 2 for that x. So the angle that you're looking at is actually 3 pi over 2. And I want you to be careful about that. Okay, and then you would go to your unit circle, figure that out, and get a value. So what would you get for a value? So here's my unit circle. Down here, this is going to be a 0, -1. So this has a not interesting answer. So what you're going to find is that the cosine of 3 pi over 2 is actually just 0. So in terms of my showing work, I would say that this whole thing right here. This whole thing right here is 0. So therefore my answer is going to be 0. Okay, so my reason for showing this example is not to get an uninteresting answer, but to understand that if this is what's going on for your angle, this is not the angle that you're checking out. Okay, plug it in for x, figure out what the angle is, and then use your unit circle. Okay, the other big thing that people make mistakes on is this situation. When you have a squared trig term, your best bet by far is to first write it like this so that you can then say, okay, this derivative is going to be 2 times tan x. All I've really done is taken the power rule. Then the derivative of tan x is secant squared x. And now I'm good to go. Okay, so then the other big piece is that since you're using the unit circle, you need to put things in terms of sine and cosine. So you've got to be comfortable doing that. So tan is sine x over cosine x, and secant squared is 1 over cosine squared. Okay, and then you go to the unit circle and evaluate whatever the angle is that I'm speaking about. Okay, so do your trig derivatives correctly. Don't short chase them. The other thing is if you see it's a product, so if you have y equals tan x cosine x, you're going to do the product rule for that. You're not going to just take the derivative of tan x times the derivative of cosine x. You're going to do lefty right plus righty left. Okay, so there's good practice on that circuit that we did, the 1718 circuit. I encourage you to go back and look at that. Okay, my plan today is not to give you homework, written homework, if you will. I'm going to do the notes for chapter 2, the very first section. But then what I'm going to do is after the quiz, which will be next class, I will post the homework for 2-1, and then that'll be due the class after that. Okay, I'd rather you spend time kind of going back over the 1718, the circuit review, this little review, and make sure that you're comfortable. And several of you need a little bit more practice on your trig. So I need you to take the time to do that so that you know your trig derivatives. Okay, in terms of more insight on the quizzes, you had to know how to take more than one derivative. So first, second, third derivative, know how to kind of organize yourself and take the next derivative. Then I'm asking you about average rate of change and instantaneous rate of change. That was the 1-8 material. You have to know if they say average rate of change, you are not ever taking a derivative. You are just taking this slope, change in y over change in x, and they will give you an interval. Make sure you can do those problems. That was in the 1-7 and 1-8 circuit review as well. When they say either instantaneous rate of change or just plain ordinary rate of change, you must know that is taking the derivative, and they will give you only 1 point to evaluate. So that's your other tip off. Then the last question is going to be about like a ball thrown in the air or a soccer ball kicked up in the air, a parabola equation, which will be a position function. I will ask you questions about velocity as well as about acceleration. I will ask you questions pertaining to the position, when is the ball, 2 feet off the ground? When does the ball hit the ground? So you have to know, based on the wording of the question, am I asking you for time? Am I asking you for position? What is the question? Do I need to take the derivative? Do I not take the derivative and just find the roots of the function? What do I do with that? Okay, so, and that's all it is. So it's 5 questions. I made it just 30 points. It should, I'm expecting great things. So don't disappoint, because I think this will help many of you kind of finish where you want to finish. Okay, so any other questions on what we're doing for the quiz? So we'll do that at the start of next class, and then I will post the homework for you afterwards, and you should be able to get most of that done and get your quiz done as well. Okay. So why don't we go ahead, if you can go into Google Classroom and download the notes packet. We're finally in chapter 2. So go ahead and download that, and we will go over the notes for only 2-1. And then I'm going to give you the opportunity to ask me more questions. If you want to have a little bit more support on the reciprocal functions, what they are, how do they work, or what the derivatives are, any of those questions, any of the physics type questions, we can pursue at the end of the notes, okay? So for right now, just go ahead and get your notes downloaded for chapter 2. And I think
Dr. Riley,
Uh-huh.
we're
Okay.
not having like a big chapter 1 test, are we?
We are not. We are not.
Okay, thank you.
Yeah, no. And I said to the other class that if we were like in school normally, we would have a big chapter 1 test that would involve doing some limits as h goes to 0 and all of that stuff. But this is just not the scenario that I want to be doing that. So we're just going to do quizzes.
Okay, thank you.
Okay, you're welcome. So in the meantime, I will get my notes up and see where we are with that. So just download it into, you should make a chapter 2 for your calculus just to keep everything straight. And we'll take notes about that. So I'll give you a second to get that downloaded. Oh, and Olivia, really quick, I haven't had a chance to look yet, but did you do that quiz?
Quiz?
I think there was one quiz you missed, wasn't there? I would take that as a no. So let's see.
I think I did miss a quiz.
Yeah, you missed a quiz. It was like the first week, probably in December. It's 1516.
Okay.
So think about where you are. You want to have that 1516 quiz done and this quiz done before the end of the quarter, which is like next weekish. So if you want to take this next class and just do the 1718 quiz, and then we can do the other quiz later, that's okay.
Okay. Yeah, I'd probably do that.
Okay, sounds good. And David, it looked like you turned in something for me, the stuff that we had worked on together. Is that true? David, are you back in one body?
Yes.
Okay. So I saw something come across the wires that you turned in, correct? Remember we had worked on something? I think you just came in today, I want to say.
Yeah, you're right. It was this morning, and I'm pretty sure I turned it in, but I think you returned it.
Well, I think weren't we going to work on that together, and then we did, and then I think you turned it in.
Mm-hmm.
I think that's how that worked. So I will look and see what you turned in. Okay.
All right.
I had
Thank
two
you.
things for you that were out because we were working on them.
Mm.
It was the 1718 review and the 18 homework is what I think we had to work on.
Yeah, I think I forgot about that. That other one.
Okay, well, see what you want to do with that.
Thank you.
Okay, so is everyone else ready? We'll go through these notes. Hopefully my pen will not be glitchy. Okay, I think I'm going to plug in my iPad too. Hang on, let me just get my wire. So we had exciting news over break. So we have grandchild number 2 coming in August. So that was good. Grandchild number 1 will be 2 in July. So it's my same daughter having her second one. So that's pretty exciting stuff if you're a mom, which none of you are, plus you're not that excited about it, but I'm excited about it. Okay, so we're in chapter 2. So chapter 2, well, chapter 1, just to recap, chapter 1 was not just chapter 1. It really was chapter 1 and chapter 8. So for a little bit, we're going to take a little bit of a reprieve from Trig as we start chapter 2. So chapter 2, we're going to be looking at functions, and we're going to be really trying to analyze the functions using our algebra 2 skills as well as our calculus skill. So this first part is more algebra 2, but we're going to talk about it in terms of calculus. So let's start with that. So there are many ways to describe graphs of functions, and there's 8 ways we're going to go through right now. So the first one is to say whether the function is increasing or decreasing. So that gets confusing sometimes for some people. When you use the increasing and decreasing terminology, what you're really talking about is what's happening to the y values. We say the function is increasing if y is increasing. The function is decreasing if y is decreasing. So let's just fill in what they have here. So when the function is increasing in the interval, fx is continually increasing. So if the function's increasing, then that means that f of x is increasing. Okay, so it's all about the y at that point. When the function is decreasing in the interval, what we mean is that f of x, which is the function y values, is continually decreasing. Okay, so I have many people get those things confused as we go deeper into this. So when you say a function's increasing, you're talking about y values increasing. Okay, we have what we call extreme points. In calculus, we focus a lot on these extreme points. They're also called extremum, which is singular. Okay, the extreme points are important because they function as minimums and maximums. And whether you're dealing with a business situation and you want to maximize your profit, that's a relative extreme. If you want to minimize the cost of an operation, that's a relative extreme. Those are the things that we want to focus on, and calculus really helps us do that very easily. So a regular extreme point of a function is the point at which the function changes from increasing to decreasing or vice versa. Another word for this is and this is extremum because it's going to be singular. Okay, so there's 2 examples here. They're both parabolas. So what's happening? So to the left here, the function's decreasing. To the right, it's increasing. When that happens, you have a relative minimum. So a relative minimum is the point where the function changes from decreasing to increasing. Okay, and then likewise, a relative maximum is where the function changes from increasing to decreasing. Okay, here it's increasing, the y values are going up, here it's decreasing. Okay, right here at the top and at the bottom, so top and bottom, it is neither increasing nor decreasing there. That is the minimum or the maximum respectively. Okay, so the terminology has to be precise. Okay, that brings us to the absolute maximum of a function. In terms of absolutes, you have to look at the end behavior. So a couple of things. I have things written here. So let me just see what I have written. So the absolute maximum value of the function is the largest value that the function assumes. That means it's the largest y value. Okay, the absolute minimum value of a function is the smallest value that it assumes. Not all functions are going to have max or mins. Okay, some do not have those. Functions with a max or a min value may not have an absolute max or min. So now we have some new terminology. You can have relative max and mins, excuse me, or you can have absolutes. So what's important? It's important to know if you have endpoints. Here and here you have endpoints. Here you have endpoints. Here you do not, so you would be well advised to put an arrowhead there so that you are cognizant of the fact that you do not have an endpoint. Okay, so in terms of mins and maxes, because I have endpoints, I know that this point or this coordinate pair 2, 5 is going to be an absolute max. Okay, when we talk about absolute maxes and I ask for the max value, I only want the y. Okay, see how they only give you the y value? And when you ask for the absolute minimum value, you only want the y value. If I ask you for the absolute maximum point, then you give me the y and the x. Okay, so this is going to be the absolute min down here. Okay, the fact that the function is really constrained because of the endpoints, I know that there's no other mins or maxes that are going to happen. Okay, what's happening over here? So we have another value over here. Right here, that's going to be a relative min. So right there, we have a relative min. Okay, it's not an absolute max, not an absolute min, it's relative. So as you go from left to right and you look little narrow windows, that's a min, but it's not the lowest that the function gets to. But I can still identify it as a min. Okay, look at the second function. What's happening here is I have a minimum value, and the minimum value is not on a vertex. That minimum value is at the starting point of the function. Okay, but I do have some relative maxes and mins. So I have a relative max here, and I say it's relative because since that function's going up to the right, there are definitely higher points. Here is also a relative min. Okay, there is lower points, and the point that I highlighted in orange, that is lower, but that is a relative min. All right, not the absolute, but it's a relative. Okay, so any questions on this stuff? This should be pretty straightforward, but believe me, when you bring it all together and then you try to throw some calculus on it, it gets confusing, and that's why I'm setting this foundation right now for all of us so that we all have the same language and that you have things that you can look back on to clarify yourself if need be. Okay, changing slope is a very important point. You've got to be careful. You don't want to say, if your function is increasing, that means your y values are increasing. You're not going to say your slope is increasing. You've got to be really careful about interchanging function and slope. They frequently don't go along. Okay, so look at what's happening here. So the slope of a graph can change in a really subtle fashion over time. You want to keep that in mind, and you want to be very cognizant of that. So this function is increasing. Okay, I can clearly see the function, the y values get greater and greater over time. What about my slope? Here, my slope would be the tangent lines I would draw. So the slope is kind of flat, then it gets steep, but then it gets less steep as you go up. So your slope is not increasing over time, only your function is. Your slope actually increases and then decreases. So that's why you don't want to interchange function and slope in your descriptor of a function. Okay, the next one, same idea. Here is your function. It's always going to be increasing, but look what's happening to your slope. Here, your slope is always increasing as well. Okay, but both functions are increasing. Only in the second one is the slope increasing. Okay, now look at these slope changes. Here, the slope is becoming more negative. So the function and the slope are both decreasing over time, because as it becomes more negative, your slope is decreasing. Look what's happening here. Your function is decreasing, but your slope's becoming less negative, which actually means your slope is increasing. Okay, so be careful about the terminology, because I'm going to ask you sometimes what's happening with the slope. And you can't just say, if the function is decreasing, the slope is decreasing. That's not always true. Okay, any questions on the idea about changing slope and changing function values?
I'm still a little confused why the figure 9 is increasing. Can you explain that again?
Yeah, because it's becoming less negative. So let's say if the slope here was -7, for example, maybe down here it's -3. When it becomes
okay, I
less
see.
negative, it's actually increasing, right? So
Yeah.
it's becoming less negative, which is also increasing.
Okay.
Whereas the one to the right, the slope became more negative. So it was decreasing as the function was decreasing.
Okay, I see that.
Okay, good. Okay, so then we have concavity. I think we'll just take a second and reshare because I'm very glitchy right now. So let me just do this. Sometimes it gets tired of being shared, which I can understand that. I get tired too. Okay, all right, so that did to be better. Okay, concavity. So we've discussed concavity. Concavity is very much a calculus type discussion. And so a function is concave up at a point if when you try to draw a tangent line, you always have to draw the tangent line below the function. That's how you can tell it's concave up. So here you see the tangent lines are hanging out below the function. Because if you try to put it above the function, it's going to hit the function in more than one place right away. This is concave down because the tangent lines are drawn above the function. Okay, so that's about concavity. So be comfortable with concavity. We're going to use that a lot. The concavity, so this is up and this is down, up, down. Concavity changes at inflection points. Let me just erase what I have here. So these points that I've drawn on your graphs, these are the inflection points. At the inflection point, the function is neither concave up nor concave down. It's changing. Okay, so, and there's more information in the textbook I'm referring to up here if you want to look at this in greater detail, but know that these are inflection points right here. So to the left of this first one, we are concave up, and then we're concave down here. Concave up, concave down, concave down, concave up. Okay, so here is a typical analysis that we would be doing. So this came from page 147 in your textbook. So let's figure out what's happening here. So let's use two colors. Okay, let's use orange for concave down. So my function is concave down, all here, up to, but not including the inflection point. That's concave down. Okay, let's go with a darker color. We'll go with blue. It's concave up, not including the inflection point, but all here. That's concave up. Okay, your inflection point, which is right here, that is the point 4, 4. At that point, the inflection point changes the concavity. So it's neither up nor down. Okay, so you would limit it. So you would say, I'm concave up from 4, but don't include the 4, and that's an x value, all the way to infinity. And then I would say that I am concave down from negative infinity up to 4, but not including 4. Okay, remember that the parens means you don't include that value. If I were to include that value, I'd have a bracket. That's my interval notation. Okay, and then you'd always want to identify your inflection point. So my inflection point will always be a point. So it will be two values, x and y. And in terms of how the intervals work, this 4 is the one I'm talking about. You write it in terms of your x values. So this is the more important of the 4s. It's unfortunate that the point is 4, 4, but that happens sometimes.
Wait, why is the inflection point at 4, 4?
Because that's where, you see how the concavity is changing there?
Yeah.
To the left, it was concave down, and then to the right, it's concave up. And that happens at the point 4, 4.
Okay.
Do you mind drawing, like, for the concavity, do you mind drawing like a tangent line just like on a couple spots? Just so I can
Yeah,
visually.
there's one there at the max. So here's another one. Notice it's always going to be above. Then when I draw it on the concave up section, I'm always going to draw the tangent line below. Because if you try to draw it above, you're going to hit the curve in two places very quickly. And by definition, a tangent line only hits the curve in one place. So we can talk about more features of this. So you have a max here. You have a min here. These are both relative because my function is going on forever and ever to the left and to the right. And therefore, there'll be additional places that will have either greater y values or lesser y values. Okay, so if you want to say, what's the max value? You would only say 5. You wouldn't give me the point. What's the minimum value? You would only say probably 3.5. You wouldn't give me the coordinate pair. When they ask for the maximum value, they're asking for the maximum y value of the function. Okay, that's important. If they asked you for the maximum point, then you would give the x and the y. Notice that at the max and at the min, your first derivative is going to be 0. Okay, so that's important too. So why don't we say f prime of x equals 0 at the relative max and at the relative min. Okay, that only happens when those are vertices. Another interesting thing, and I'll change color just to make it look different, f prime prime of x will equal 0 at the inflection point. Okay, so you can mathematically determine where your inflection point is by setting the second derivative equal to 0. Okay, you can mathematically determine where your relative max and mins are by setting the first derivative equal to 0. So that will come up a lot, and we'll be going over that many, many times. Okay, then that brings us to more general observations about functions that are typical algebra 2 material. So a y-intercept is defined as the point where the function crosses the y-axis. Okay, so if my function is a line, that could be my y-intercept. So how many y-intercepts can a function have? What do you think?
1.
1. And how come you said 1 so confidently?
Because if it was more than 1, it wouldn't pass the vertical line test.
Yep, exactly. Okay, so it can only have 1, and it's because needs to pass vertical line test if it is indeed a function. Okay, they just issued a citywide curfew for DC starting at 6 p.m. So don't go down to DC later on tonight. So X-intercepts are a whole different story. Okay, so the X-intercept is the point where the function crosses the x-axis. Okay, so this could be an example if I have a polynomial function. All these places it can cross the x-axis. So what's it called when it crosses the x-axis? It can be called several things. Give me some of them. So give me one thing you can call it when it crosses the x-axis. So Gavin, what's whoever's saying? Go ahead, Jonathan.
A 0.
Yep, a 0 is good. Okay, so it can be called a 0. Give me something else. What else could it be called?
A root.
A root, that's good. Okay, and the other class said it can also be called just an X-intercept, right? So all those things are common terms. Okay, we will frequently call them the zeros of the function in calculus, but they also can go by roots and X-intercepts as well. Okay, do all functions have to have an X-intercept? And give me an example if you say no. Say yes.
No.
So if you say no, what kind of function would not have an X-intercept?
Y equals 2.
Yeah, that's good. So a line that's above would not have it. How about a parabola that doesn't come down at all? That would do it as well. So this is a big old no. Okay, so there are other ways that you can have an X-intercept not be in play, but those are two good examples. In terms of undefined points, page 147 covers this as well. Think of functions that would have an undefined point. So for example, you can't have a negative under a radical. So if you have a radical function, x has to always be greater than or equal to 0. Anything to the left is undefined. If you have a rational function, you can't have your denominator equal 0. So in this case, x cannot equal 0 because having a denominator equal to 0 gives you an undefined function, and therefore that's your undefined point. Okay, so those are two good examples there. Asymptotes are something else we're going to talk about. We talked about some of these in terms of limits. Remember when we talked about horizontal asymptotes being the limit as x goes to either positive or negative infinity? So that would be an asymptote. So here would be an asymptote as x goes to positive infinity. And then here you can get an asymptote as x goes to negative infinity. Okay, both those functions as asymptotes. Rational functions will get you vertical asymptotes as well. So what if you had a function that was, say, y equals x plus 4 over x minus 7. At x equals 7, you would have a vertical asymptote. Okay, and I don't know what this is going to look like. Let's say it looks like this. And right here at 7, you would have a vertical asymptote. So those are the different ways we can describe functions. Those are all 8 ways. So here I just summarized them for us. And in the summary, I said the red ones are really important for calculus. So other things, asymptotes, undefined points, they come up. But really things like describing how a function is increasing and decreasing, knowing where inflection points are, knowing concavity issues, all that's really important for calculus. And what we do is we do function sketching that are based on our derivatives of functions. And that is kind of fun because you really can get a good sketch of a function just knowing about where the derivatives are occurring. And we will do that in 2.2. So that's coming pretty quickly. Okay, so that's all I wanted to do today. Because, as I said, I wanted to get us started in chapter 2. There's not going to be any homework on this right now. I will have us analyze some functions using these 8 steps, and that'll be our homework after the quiz next class. Okay, so does anybody have, now that you've had a little bit of time to think, do you want to look at anything in terms of the trig or anything else we may have covered before break that will pertain to 1718? So I'm thinking taking derivatives of trig functions, evaluating trig functions using the unit circle, taking first, second, third derivatives, knowing the difference between average and instantaneous when they speak about evaluation of functions. Anything come to mind? There's a lot of silence. Go ahead.
On number 1 of the homework last night, I was struggling what to do because if you remember, it was the tan that we changed to the sine over cosine, and I didn't know like what to do when looking at a unit circle. Like what?
Okay, so let's do that together. So that's a good one. Okay, so that was the exploration activity, which is here. And it was this one, right? Okay, so did you catch the fact that you have to use the power rule and the chain rule? Were you okay with that?
Yeah, I was good with that.
Okay, so then the next thing is now I want to draw my little unit circle, but I want to figure out what angle I'm going to be evaluating. So because my angle is x and the x value is pi over 3, it'll definitely be pi over 3. Okay, so what I'm going to do is just do this. Pi over 3 is the top one. So this is pi over 3. And when I do my little labeling, I count 1, 2, 3, and then take the square root of all the numerators. Okay, so I know that for pi over 3, it looks like my cosine is going to equal 1/2, and my sine of x equals root 3 over 2. Are you okay with that?
Yeah, I'm good with that.
Okay, so then let's evaluate y prime of pi over 3. So that's going to be 2 times, so the sine of pi over 3 is going to be root 3 over 2. And then you're going to divide that by 1/2. And then times 1 over cosine squared of x. So since cosine of x is 1/2, 1/2 times 1/2 is 1/4. Okay? So this 2 and this 2 can cancel. So now I have root 3 divided by 1/2. That's the same as root 3 times 2 over 1. So this first term becomes 2 root 3. And then this 1 divided by 1/4 is the same as 1 times 4 over 1. So this is times 4. So my y prime is going to be 8 root 3. And that's what I'll get for my answer. Okay, so they didn't ask you just for that. That's going to be your slope, 8 root 3. They want the tangent line. So remember that's y minus y1 equals the slope times x minus x1. So y minus y1 was 3. My slope I just figured out was 8 root 3. And this is x minus the x1, which is pi over 3. Okay, so that would be the answer that I'm looking for. I gave you the x and the y. You really just had to work to get the slope. Does that seem pretty straightforward?
Yeah, that's fine. I had just gotten a little lost in the middle when there was like the dividing, all the roots and everything.
Yeah, so think about how you divide fractions. You know that the 2's up top that I canceled first, that's easy. Then say to yourself, okay, I have root 3 divided by 1/2. I never really divide fractions. I multiply by the reciprocals. So root 3 divided by 1/2 is just root 3 times 2. That's where my first term came from. And then 1 divided by 1/4 is the same as 1 times 4, and therefore I have a 4. And then just multiply numbers together, the radical comes along for the ride.
Yeah, that makes sense.
Okay, good. And then, you know, always be on the lookout for those powers, because the powers will mess you up if you don't view it as indicating you have to do the chain rule. Do the power rule first and then do the chain rule. So when you have a trig function raised to a power, you will always have at least 2 trig functions in your answer for the first derivative. Okay, that will always happen. Sometimes you'll have 3 if it was cosecant squared or secant squared. So anyway, you've got to, you know, be on the lookout for that. So anything, how are you guys with knowing the reciprocal functions and all of those good things? So are you, so let's just go through some of those. So I know that, so we have sine, cosine, and tan. Okay, so sine and cosine are going to be your bread and butter in terms of the unit circle. Tan is equivalent to either sine x over cosine x or secant x over cosecant x. Okay, they're all equivalent. So then you've got to know that cosecant x is 1 over sine x. Secant x is 1 over cosine x. And then cotan x is just going to be either cosine x over sine x or cosecant x over secant x. Cotan's always c over s, and tan's always s over c. Okay, so those are big things to remember. Then the other thing you want to definitely know are your derivatives. So the derivative with respect to x of sine x is always going to be cosine x. The derivative with respect to x of cosine x, here's a c. The second you take a derivative of a c word, it's going to be a negative. Derivative with respect to x of tan. Tan and secant will always give you squared terms. So that's going to be positive secant squared x. And then the derivative with respect to x of cosecant x will give you negative cosecant x cotan x. Derivative with respect to x of secant x will give you positive secant x tan x. And the derivative with respect to x of cotan x will give you negative cosecant squared x. So you want to keep those straight. Then you want to be aware that the second your angle is not just an x, if it's a 7x, a 6x, a 3x squared, you've got to take the chain rule derivative of the angle. So that's going to be a part of your answer. The other thing you want to know is that if you have, like, say, sine of 4x, your angle at the end of the problem will still be 4x. You're not going to end up having an angle be just plain old x because you've taken the chain rule. The 4x will always stay with the angle. So at the end of your problem, you'll have the same angles that you started with. So those are the big things that come to mind in terms of trig. Now that you know product rule, quotient rule, power rule, you can be discerning when you use them. So that means that if you have something like y equals 5 over x plus 2, you don't have to do the quotient rule to do that. You can do the power rule and bring up the x plus 2 as an x plus 2 to the -1. That probably is the wiser way to do it. It'll be less complicated for you. Okay, there's no valor in making your problem as complicated as possible. Before you start work on any problem, if you can simplify it in some way, definitely do that, because that will help you have fewer terms to work with. And that's always a bonus. Be careful about your negatives. Be always on the lookout for those negatives. They will mess you up sometimes. Make sure that if you're taking a derivative and you have a negative in it, you write it so that you know it's not a subtraction sign, that it's actually a multiplication of a negative sign. So just be careful with that. I would make sure that you write neatly, because that will always help you. Use scrap paper whenever you want to, because if you can't read what you're doing and follow the steps, you're going to be in trouble. Okay, notation is really not optional. You've got to use good notation. So if you're using prime notation, you've got to make sure that you have actually taken the derivative. A lot of times people will, do something like this. You'll have y equals radical x, and then all of a sudden they're going to say y prime is x to the 1/2. Well, it's not. All you've done is rewritten. So make sure that you do not use prime when you have not yet taken the derivative. So when you are rewriting things, as you should to get things going, make sure that you are keeping your notation nice and clean, because that will separate the men from the boys, the women from the girls. So anything else you think of? I can talk all day. I don't know if you want to listen all day, but those are some of the key points I want you to go back and look at. So I would not worry about this section right now. I would just focus on everything 1718. It's been a while since we've done it because of the break. So I encourage you to go back and look at anything that pertains to 1718, and that get yourself comfortable on trig and derivatives and notation in general. Okay, so that's kind of all I have. So I can let you go a few minutes early, give that life back to you. Email me if you get yourself confused some way, and I can unconfuse you. Otherwise, we'll do the quiz next class, and then I'll give you the 2.1 homework after that. Okie doke.
Can you post the circuit, like the answer key to the circuit?
Yes.
Thank you.
Yeah, I can do that. Okay, you're welcome. You're welcome. So have a good afternoon. I'll work on posting that now while I'm thinking of it. And then anything else you need, just email me. Circuit.
Thank you.
Okay, you're welcome.
Thank you.
Bye.
Thank you, Dr. Riley.
You're welcome. Bye-bye, guys.
Thank you.
Dr. Riley,
Yep.
I have a quick question. So could you post like on the stream or something for classroom, like the stuff that we should review, like the things that you went over earlier, like 1.7, 1.8? Can you post those or no?
Yeah, I'll post that list. Okay, so I'll do it on today's class, and I'll also post the circuit answer key on today's class. Okay,
cool. And then there's no homework for tonight, right?
Right, there's no homework. I want you to go back and look at things so that everything's fresh in your mind for the day's quiz.
Awesome. Thank you, Dr. Riley.
Okay, you're welcome. Bye-bye.
Bye.
Jonathan, are you good?